All right, so the assignment that you did over the weekend was all about these Lewis dots and getting these Lewis dots kind of familiar to understand how valence electrons fit into this overall scheme of bonding. And we're going to start with ionic compounds because ionic compounds are easier. Because in ionic compounds, all that we are going to do is we're going to see Lewis dots taking hold to either vacate, get rid of all of the Lewis dots in the case of a metal, or in the case of a non-metal, add enough Lewis dots, add enough extra electrons to completely fill up all 8 of those spots. And remember, it's because of the electrostatic attraction, the fact that we have a positive ion and a negative ion, that is going to allow these guys to stick together. That's what's going to drive this whole process. So it is a literal transfer of electrons from one to the other to create these compounds when we make ionic compounds. And if we have more than one, like if we had magnesium with chlorine instead of sodium, what we would see is that to get rid of both of the electrons in the magnesium, one chlorine's not enough. That first electron goes, chlorine gets filled up. I end up with a magnesium that still has a dot and a positive 1 charge, and a chloride that is completely filled. So I know that that chloride's not going to grab any more electrons off of it. What do I have to do? What happens? Well, we talked about the idea in nomenclature about charge balance. Now we have a mechanism for why that charge balance has to exist. Magnesium isn't at its full octet, only losing 1 electron. It's got to lose them both. The only way that it can lose them both is if it has 2 chlorines to give the electrons to. 1 over here to this one, 1 over here to that one. That's how we can get the magnesium plus 2 ion. That's how we end up getting 2 chloride minus ions as well. So we discussed this already in nomenclature, this whole idea that there has to be charge balance. But now we see in action through these Lewis dot diagrams why that has to be the case. Not just from a balance standpoint, but from an octet rule standpoint. When it comes to molecular compounds, however, it's not quite as easy as with the ionic, because with the ionic, we can clearly see this one has an octet and this one doesn't. This one's just going to add electrons until it gets an octet. This one's just going to lose electrons until it vacates the level and takes up the octet behind it. With molecular compounds, because they're sharing electrons, it's not quite as cut and dried. How do I look at that compound, ammonia, and know for certain that every single one of those atoms has a full complement of electrons? And what do those lines in between each of the atoms represent? Well, we're told those lines represent covalent bonds. Those covalent bonds represent two electrons being shared between each atom that is being held together by that line. So the nitrogen has two electrons from that line. The hydrogen has two electrons from that line because those two electrons are shared between them. And so if I look at this from the standpoint of the hydrogens, each one of these hydrogens has one line between it and the nitrogen. So they each are holding two electrons, which for hydrogen is good enough. Remember, hydrogen obeys the duet rule because it's in that first energy level. First energy level holds two electrons and only two electrons anyway. So hydrogen and helium have no need for 8 electrons. They only have need for 2. So hydrogen's perfectly good with those 2 electrons that are being shared. For the nitrogen, I can see that I've got 2 electrons from this, 2 electrons from this one, 2 electrons from this one. That's 6 electrons around that nitrogen from its bonds. This extra set of dots there, those are unshared pairs of electrons. Those belong only to the atom that they are attached to, which in this case is nitrogen. So if I add those 2 to nitrogen's group, I now have 2, 4, 6, 8. That's the 8 electrons that the nitrogen needs to fill out its octet. So the way that we draw Lewis structures for molecular compounds is different. And it's got some different conventions to it. But there is a process that we can undertake to make it easier to see and to help us to draw these ourselves. And the process is this. To draw a simple Lewis structure, we need to do 4 things. First, we need to determine how many valence electrons there are. We can do that by looking at the chemical formula, looking at the periodic table, and adding it together. In the case of NH3, we had nitrogen, which we could look at the table and say, okay, nitrogen has 5 valence electrons. And we can look at hydrogen, which is in group 1, and say, okay, well, each one has 1, and there are 3 of them. So there should be a total of 8 electrons in that molecule of ammonia. From there, we need to arrange the elements to show how that they are bonded together. How do we do that? We need to determine the center atom. And the center atom is going to be the one that is the least electronegative. Remember at the end of Friday's lecture, we talked about electronegativity, that ability for electrons to be drawn to an atom when it's bonded. The center atom is going to be the one that has the least attraction. Now, without pulling out your Linus Pauling electronegativity scale, how do you know that? Rough location. Fluorine is the most electronegative element. The further it is from fluorine, the less electronegative it is, the more likely it is to be the center atom. If it appears to be a tie, choose the bigger one. So for example, chlorine and oxygen both appear to be the same distance away from fluorine. They're one box away. Chlorine would be the center atom in that circumstance in most cases. Some exceptions, but most cases. And the reason is it's bigger and it's going to be less electronegative as a result. Now, in case of ammonia, there's only one option. Hydrogen cannot be a center atom. Why can't hydrogen be a center atom? It doesn't obey the octet rule. To be a center atom, you have to make more than one bond. Hydrogen can only make one bond. So once we have that center atom, we're going to make a simple structure. That simple structure is going to start with the center atom in the middle and draw single bonds everywhere else to every other element. Then we're going to complete the octets. We're going to make sure everybody has an octet. And we're going to do it by using those lone pairs of electrons. That's what would give us what is called the simple structure. Now, that simple structure may not be correct. How we check it is what step number 4 is all about. Count up all the electrons in that simple structure and compare it to what we calculated in number 1. If they're the same, the structure is good. We don't need to do anything else. If they're not the same, we need to make a modification. One of two things needs to happen. If this number is bigger than what we should have, then we need to add more bonds. For every extra pair of electrons that we are over, we need to add one more bond. So for 2 electrons over, we need to add one more bond. For 4 electrons over, we need to add 2 more bonds. For 6 electrons over, we need to add 3 more bonds. And so on and so forth. If we don't have enough electrons, so let's say that we're supposed to have 34, but we only get 32 in the structure, or 2 extra. Where do those 2 extra go? In the middle. The reason they go in the middle is because, again, that center atom is usually bigger, and it's going to have a place for those extra electrons to go. Smaller atoms on the outside can't and won't. All right, so let's get into doing some examples. Here I have chloroform. Chloroform is used as an anesthetic. It's got the molecular formula CHCl3. We want its Lewis structure. So the first thing we do, we need to figure out the number of valence electrons. Carbon has 4, hydrogen has 1, chlorine has 7, and there are 3 of them. So a little bit of quick math, 4 plus 1 is 5, 7 times 3 is 21, 5 plus 21 is 26 electrons. Now we start with the simple structure. To do the simple structure, we need to figure out the center atom. Center atom is going to be the least electronegative, the one furthest from fluorine. And so throwing out the hydrogen as an option, it's either carbon or chlorine. Which one's further from fluorine? It's not hard. Thank you. Carbon. So carbon needs to go in the middle. Our simple structure is going to draw single bonds from that carbon to the other four atoms, the three chlorines and the hydrogen. Our simple structure is also going to fill out the octets of everything else. So chlorine, right now I have 2 electrons in the bond. I need 8 in total. So I've got 6 dots that are going to go around each chlorine. Hydrogen has 2 electrons from that bond. Hydrogen only needs 2 electrons. It's done. Carbon has 4 bonds. 4 bonds times 2 electrons each is 8 electrons. So it's done as well. So this is our simple structure of chloroform. Now let's see if it is the correct structure of chloroform. How we do that is we have to count. So I've got 2 electrons, 4, 6, 8 in each of the bonds. Now just going around 10, 12, 14, 16, 18, 20, 22, 24, 26. 26 electrons in the structure, which matches the 26 electrons I'm supposed to have. This single bonded structure is the correct structure. I don't need to do anything else with it. So sometimes it really is just that simple. Figure out what goes in the middle, draw out all your single bonds, fill out the octets, and it works beautifully. Any questions with this example? Okay, let's look at another example. This time I have acetylene, C2H2. So step 1, I've got 4 for carbon, and there are 2 of those. And I've got 1 for hydrogen, and there are 2 of those. 4 times 2 is 8, plus 2 more is 10 electrons. Now, this one's a little bit more complicated for a couple of reasons. First of all, there is no single center atom. When we see organic molecules such as these, where we've got multiple carbons in the same compound, that is a sign that we're going to make a chain. So I just want you to be aware of that, because some of the skill builder questions that you're going to do at the end of this week, some of the questions that you might see in assignment 4-3 or in the homework might be some of these chain compounds. So if you see multiple carbons, what you need to think about is making a carbon chain, carbon to carbon, and then kind of filling out the rest of the stuff symmetrically, evenly as possible. So in this case, I've got a carbon-carbon chain. I'm going to fill out my hydrogens evenly, 1 on each carbon. And I need to fill out the octets now. Hydrogen is okay. It only has 2 electrons. This carbon here on the left has 2 and 4, so it needs 6 and 8 to fill out its octet. This carbon also has 2 and 4. It needs 6 and 8 to fill out its octet. And again, the hydrogen's okay with its 2 electrons. So this is our simple structure. Let's see if it's any good. 2, 4, 6, 8, 10, 12, 14. Uh-oh. We've got 14 electrons in this structure. We're only supposed to have 10. We're right in the thick of that step 4 now. What do? We need more bonds. How many more bonds? Remember, for every 2 that we are over, we need 1 more bond. We're 4 over, so we need 2 more bonds. So where can those bonds go? Well, they can't go to either of the hydrogens, because that would mean that hydrogen now has 4 electrons instead of 2. Hydrogen can't take any more than 2 electrons. So they have to go between the carbons. So those extra 2 bonds between the carbons mean that that single bond that was there is now a triple bond. There are 6 electrons being shared between those 2 carbons. And then single bonds. With our refigured structure, we still need to go through all of the other steps. So we need to make sure, does everybody have an octet, or do I need to add more dots? Well, hydrogen again is okay. The carbon now has 2, 4, 6, 8 around it. 8 electrons in bonds means it doesn't need any dots around it. Same thing with the carbon on the other side, 2, 4, 6, 8. It has no need for extra dots. It's completely filled as it is. I can recount now. 2, 4, 6, 8, 10. This structure now has 10 electrons, which matches our 10 electrons that we're supposed to have. We're done. So when we come into situations like this, where we have a disagreement between our simple structure and our correct number of electrons, this is how we handle it. We have to evaluate what we're dealing with. Questions about this one? All right, let's take a side trip for a minute. Now, if we go through the process of drawing ozone, O3, would have 18 valence electrons. And if we do the structure up, what we will find is that we end up getting a structure that looks like this, where the single bonded version so our simple structure here ends up having 20 electrons in it. Now, under the rules that we just talked about, we have to turn 1 extra bond out. The question is, do we turn that extra bond on the left-hand side or on the right-hand side? So which one of these structures is actually correct? Left? Right? Neither? Both? The answer is one of those. What we're getting here is something called resonance. Resonance is a phenomenon that exists when we have more than one way of drawing a Lewis structure and that Lewis structure being correct. Usually we see resonance when there is an arbitrary nature to the placement of a double or a triple bond, as was the case here. Bond could have gone on the left, bond could have gone on the right. The two structures would have looked identical to each other either way, just rotational mirror images of each other. So they're the same. Now, what actually happens, and this is where it gets a little bit funny, is that those electrons don't actually exist in either place all the time. Those electrons, that double bond, is kind of moving around. We call that delocalization. That means that the electrons aren't fixed to a particular location. They're delocalized. They move around. In organic chemistry, we see this with benzene. Benzene rings have a structure of double bonds and single bonds alternating around this 6-membered ring. And what happens? Those double bonds and those single bonds move around that ring, and all 6 of those electrons end up being delocalized, moving around. In this case, we only have 2 electrons that are delocalized. But what it means for this structure is that the structure doesn't actually exist as the left or the right. It exists as both simultaneously and kind of neither simultaneously. When we talk about the bonds themselves here, what we will find is that the bonds themselves are exactly the same size and have exactly the same length, exactly the same strength because of that delocalization. And their bond length and strength is not going to be like what we see for other oxygen-oxygen bonds. It's going to be slightly stronger than an oxygen single bond, but not quite as strong as an oxygen double bond. It kind of fits in the middle. Why does it fit in the middle? Because it doesn't really have all of the full extra bonding of a double bond, but it's got more bonding than a single bond. So let's do a practice with these resonance structures. Let's look at nitrate ion. With the nitrate ion, I have 5 from the nitrogen, 6 from each oxygen, and this -1 charge means I have 1 extra electron. So when we are dealing with charged compounds, we can either add that charge to the total if it's negative, or we can subtract that charge from the total if it's positive. In this case, it's negative, so we're going to add that -1 charge. 24 electrons is going to be my amount here. Nitrogen is less electronegative than oxygen. So I'm going to start with my simple structure here and fill out all of the octets. So 6 electrons around each of the oxygens. And since the nitrogen here only has 3 bonds, 6 electrons, the nitrogen is going to need a set of electrons as well. to get it up to 8 also. If I count it out, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I find that I'm 2 electrons over. What do I do with those 2 electrons? Well, it's the same thing we've been doing in each of the last 2 examples. If I'm over, I need to add a bond. This time I'm only 2 electrons over, so I only need to add 1 extra bond. But the question is, where do I add that bond? That's where the resonance comes in. It is equally likely that that extra bond will be on the left as it would on top or on the right. I just need to fill out the octets for everybody. And since the nitrogen now has 4 bonds around it, I don't need that lone pair on the nitrogen anymore. So in this case, the nitrogen to oxygen bond, that double bond is shared over 3 different areas. Now, how do we show that these 3 structures are equivalent to each other? We can connect them with double-headed arrows to show that they are resonance structures of each other, that they are all equivalent. And there's one other thing that we need to do. Since this is a charged molecule instead of just a molecule, we need to show that charge in some kind of way. Way that we're going to do that, we put it in brackets. And we put the charge on the outside of the brackets. Now, there's another way to do it as well, but we're not going to get to that today. That's called formal charge. And as far as your homework and smart work are concerned, they like you to use formal charge more often than bracketing. But bracketing is where we'll start for today. So as far as the chapter 4 quiz is concerned, you'll need to know formal charge in the sense of formal charge helps us to pick the best structure when we seem to have an arbitrary choice that isn't resonance. And we'll talk about that on Wednesday. But that would be when you need to show formal charge is that kind of thing. But as far as like showing a charged molecule, if I ask you to draw I3 -1, which is on your sheet here, all you have to do is bracket that I3 and put a -1 charge on. Okay, I want to end today with just a little discussion of some places where the octet rule does not apply. So there are two primary reasons that the octet rule would not apply in a situation. One of those reasons would be where we have some sort of electron deficiency. In particular, group 13 and group 2 to a lesser extent are places where we would notice this. Now, when we talk about formal charge, the reason for that electron deficiency will make a lot more sense. So we'll kind of put that one in our back pocket until Wednesday. But just understand that it does exist. Now, as far as this is concerned, there are no electron deficient molecules on this page. But there is at least one example of one that breaks the octet rule by going too far. Where we see this primarily is when we have large, relatively low electronegative substances, elements that are bonding with highly electronegative elements. So things like sulfur hexafluoride, where sulfur is breaking the octet rule to accommodate those extra fluorines. There are a couple of rules for this. First of all, you can only do an expanded octet if you are an element that is in the third row or below. So substances like carbon, nitrogen, oxygen, they can't break the octet rule. The reason they can't break the octet rule is they don't have d orbitals available in that same energy level. Remember, the d orbitals show up in the third energy level. That third energy level is where we can drop those extra electrons if the situation requires it. Now, the other thing also goes back to formal charge. Formal charges generally get improved when we break the octet rule in this kind of way. Again, we'll talk more about that on Wednesday. The other place where we can see it are in particular with nitrogen compounds, phosphorus compounds, where the simple mathematics of the molecule does not allow us to have a full octet. If I have an odd number of electrons in the molecule, there's no way I can get an octet for everybody. I'm going to end up having something with an odd electron in it. That odd electron is always going to go on the nitrogen group substance, because this is where we see it. It's going to go on the nitrogen. It's going to go on the phosphorus. It's going to go on the arsenic. And so that's where we're going to close for today.